Welcome back. So we're going to continue on talking about Chapter 7, and Chapter 7 is focused on decimals, ratios, proportions, and percents. So we're going to start off section 7.1 here, talking in detail about decimals. And so decimals are used to represent fractions, but in our usual base 10 notation. So let's start off by looking at an example of a decimal here, this 3,457 and 968 thousandths. Okay, so here we have kind of listed all of the places below, and we can think of this similarly to how we did in an expanded form when we weren't looking at decimals, when we were just looking at whole numbers. And to do so, to get from the ones place to the tens place, I was going to multiply by 10, right? So kind of going this direction, I multiply by 10, and going this direction, I multiply by another 10, and so on. But when we go to the decimal representation, what we're really doing is we're moving the other direction, so we're dividing by 10 each time we go one decimal to the right? And so kind of extending that back to our kind of our whole number representation, we're doing really the same thing if we just go the other direction, right? If I go from thousandths to hundredths, I'm really dividing by 10. Okay, so we're extending that idea. And so this helps us to write a number in expanded form so that we can better understand it. So for example, this number in our example here, this is the thousands place. So the 3 is associated with the thousands place. So I would multiply 3 by 1,000. And 4 is associated with the hundreds place. So I would multiply 4 by 100, or 10 squared. And 5 by just 10. And 7, of course, just by 1, since it's in our ones place. And then when I continue this on with my decimals, the 0.968, 9 would be multiplied by 1/10, and 6 is going to be multiplied by 1/100th, and 8 is going to be multiplied by 1/1000th, right? So we can think of this as 1 over 10 cubed, and this is 1 over 10 squared, and of course this is just 1 over 10 to the 1, and so on. Okay, so this is how we would write our number in expanded form for a decimal. We can also represent these decimal numbers visually using a hundredth square. So now instead of thinking of this whole square as 10 by 10, and representing 100 units, I'm going to think of this whole square as representing 1 unit, okay? And it's broken into hundredths, all right? And so this blue column here is going to be 1/10 of that square, so that represents 0.1. This little blue square here just is is 1/100th of that square, right? Since there are 100 little boxes, so that represents 0.01. So here's like a nice visual representation of decimals using a hundredths block, okay? And so kind of we can continue on with this example. If I color in these 4 columns, this represents 0.4 or 4/10, or in other words, 4 over 100. Sorry, I'm trying to erase that. There we go. 4 over 100, and so on. And same thing with this last example here. Here we've just colored in 7 of the squares, so that represents 0.07 or 7/100 now. Okay, so that's a nice way to visually represent what these decimals mean. And so so there's this obvious connection, especially when you look at the 100 square, between decimals and fractions. It's just a decimal is just a different notation for the same concept. And so let's try to we want to be able to go back and forth. So given these fractions, let's try to write them as decimals. So here, this is 7 over 100. So this is 100, and we can kind of see this most clearly if we think about this in my expanded form. It's saying I have 7, if I kind of look back at this example in terms of the expanded form, it's saying I have like 7 of these 100th pieces, right? So another way to write this is 7 times 1 over 100. So be careful, these parentheses are important here. This is 7 times 1 over 100, not 7 and 100th, right? So this is not a mixed number. Using the decimal notation, this is 0.07. Okay, so we can extend this along, and this number 123 over 10,000. Let's see, we have 1, 2, 3, 4 zeros. So basically, another way to think of this is, so we're going to have 123 over, or times 1 over 10,000. So I'm going to move the decimal to the right, to the left 4 places. Right there, we can imagine looking at 123, there's a little decimal here on the far right, and I'm going to move it 1, 2, 3, 4 places, right? So I need to add another 0 in here. So in other words, my decimal notation is 0.0123. Okay, so now when we look at a number like 1 and 7/8, it's a little more complicated to go into the decimal notation because I'm not over something that's already nicely written as 10 to some power, right? So remember this notation here, 1 and 7/8, is different. This notation here is different than this notation here, right? So 7 with the parentheses here, this means 7 times 1 over 100. In example 3, we have this means 1 plus 7/8, right? That's the mixed number. So be very careful about kind of what's implied by these notations, whether there's some sort of parenthesis or the operation is implied to be multiplication as in example 1 or addition as in example 3 here. Okay, so what we would like is for this fraction here to be over not 8, but have a denominator of 100, right? So that's exactly what we're going to do. We're going to try to change the denominator to be 100 instead of, or some power of 10 as opposed to 8, right? So let's rewrite this as 7. And I think it's easiest if we look at 8 in its factored form. So remember, 8 is just 2 cubed. Great. And so to make this denominator some power of 10, well, in order to multiply 2 by something to get 10, we'd have to multiply it by 5, right? So I have 3 2's here, so let's multiply it by 3 5's. And whatever I do to the denominator, I have to do to the numerator. Otherwise, I'm changing the value of my expression. So I'm just going to erase that there. So I'm going to do the same thing to the numerator. So I'm really just multiplying by 1 here. Okay, and now let's just go ahead. We can multiply this out. The bottom is really just using rules of exponents. It's 10 cubed. And if you wanted to multiply this out, I think you get 875 or 1 plus 875 over I think 10 cubed should be 1,000. And so this is 1.875. So the trick here is to turn the base, which was, or sorry, the denominator, which was 8, into some power of 10. And we did that here by multiplying by powers of 5, since we already had powers of 2. Okay, so here in this last example, we're kind of going to do the opposite, right? We have some powers of 2 in the denominator. We need some powers of 5 in the denominator to make the denominator a power of 10. Okay, so let's see. I have 3 and 2/4. Well, I have 4 powers of 2 in the denominator, so let's add 4 powers of 5 to the denominator. And when I say add, I mean multiply. Oops. And whatever I do to the denominator, I have to do to the numerator, otherwise I'm changing the value here. Sorry, I should have left a little more space. But I'm just multiplying by 5 to the 4th over 5 to the 4th. And multiplying that out, I get 1,875, so 1875 over 10,000 this time. Right? I should have 10 to the 4th in the denominator, not 10 to the 3rd. And so this should be 0.1875. Great. Okay, so those are a bunch of examples of going from fraction form to decimal form. So the thing to notice is in these last two examples, when I had a fraction that denominator was not clearly some power of 10. So in example 3, I had a power of 2. In example 4, in example 3, oh yes, I did have a power of 2. In example 4, I also had a power of 2. I need to turn that denominator into a power of 10, right? But notice, if my denominator didn't have a power of 2 or 5, but it had some other powers, like 3 to some power, or 7 to some power, so some other prime powers in that denominator, I wouldn't be able to get a nice multiple of or power of 10 in the denominator of that fraction. And so that's where we get this following theorem. So a fraction a over b is in simplest form. It has a terminating decimal representation. If and only if b, so that's b being the denominator of that fraction, sorry about that, has only 2's or 5's in the prime factorization. So that's kind of alluding to these last two examples here, where we had powers of 2 in the denominator, and I multiplied by powers of 5 to get powers of 10. I could do the same thing if I started with powers of 5 and multiplied by powers of 2 as well to get a nice decimal representation. So here's an example of we had powers of 2 and 5, so we got a nice terminating decimal representation. So basically, I'm starting with powers of 2 and 5, and then the denominator, I get a nice decimal representation. This theorem says also that things go the other way. It says if you have a terminating decimal representation, that you can write your fraction as something with 2's or 5's only in the denominator, powers of 2's or 5's, which seems maybe not super important, I guess, but what this theorem says is it basically gives us a way of taking a fraction and telling whether or not that it can be written as a terminating decimal. And when I say a terminating decimal, oops, I didn't mean to erase that, I meant to highlight it. When I say a terminating decimal, what I mean is one that like ends or repeats. I think just ends here is what our context is going to be. So, so if I want my decimal to terminate, as they do in all of these examples, I need to be able to write that denominator as a nice power of 10. So you'll kind of get a feel for this as we go through more examples and we talk about things in a little bit more detail. But I guess this is a quality that maybe you might have taken for granted and thought you can write any fraction as a terminating decimal, or not really seeing a relationship between the fractions and whether or not the decimal terminates. But there is this relationship with between that we can kind of find a pattern and a correlation between what the form of the fraction looks like and whether or not the decimal terminates. Okay, and this is the correlation that the denominator either has powers of 2 or 5. Okay, so a little bit more abstractly, just talking about ordering decimals. Probably the most intuitive way that you have of ordering a decimal is in this last method that I talk about here, is looking at the place value method. So if I'm comparing these two decimals, 0.7 and 0.23, I know that 0.7 is bigger than 0.23, right? That's what this inequality says. Since the tens place, which is my biggest place, or the tenths place, sorry, I should say, which is my biggest place value, is larger, 7 is larger than 2 in that tenths place. And I can completely ignore the fact that I have a 3 in the hundredths place of 0.02, or sorry, 0.23. And so this is probably the most common way that you would order two decimals. But there are some other ways of visualizing and understanding this ordering outside of the kind of more nuanced understanding of place value. And one thing, kind of a very nice visual, is using, again, the hundredth square. I can represent both 0.7 and 0.23 is in the hundredth square. So 0.7 would be 7 of these whole columns, right? So this is 0.7 of the hundredth square. And if I shade in 0.23 of the hundredth square, it is quite clearly a smaller region than the other one, right? And so that's what tells me that 0.7 is greater than 0.23. So there's one visual representation. Another one is looking at the number line. So if I want to represent 0.7 on a number line, I would just go out 1, 2, 3, 4, 5, 6, 7. Right? So this should be about 7. So this would be 0.7. And I could do the same thing with 0.23. And it's going to be 1, 2, like a little bit bigger than 2 of those tick marks, right? And I can see using this number line that 0.7, that line is longer than 0.23. So that also tells me that 0.7 is bigger than 0.23. And finally, the last way that we can understand how to order decimals is by turning them into fractions, if possible. So I can look at 0.7 and I know that is 7 tenths. And I can look at 0.23 and I know that is 23 over 100. And in this current form, it's not super easy to compare them because they have different denominators. So a nice way to deal with that is to multiply this first one by 10 over 10 so that my denominators will be the same. So this gives me 7, this is equivalent to 70 over 100. And now that they have the same denominators here that are both 100, I can see, oh yeah, 0.23 is definitely smaller than 0.7. Okay. Because 23 is less than 70. Okay, so 4 different representations and ways to understand ordering decimals there. So 2 last little things to touch on with decimals before just talking more about operations on decimals would be thinking through our mental math techniques. And most of the mental math techniques we talked about with whole numbers carry over really nicely when we talk about decimals. And so one of them in particular being compatible numbers. So we have different types of compatible numbers now. We're going to look at things that maybe add to whole, or decimals that add to whole numbers, but still like the same basic idea will be employed. So for instance, in this example where we are adding 1.7 plus 3.2 plus 4.3, I might notice that if I take 0.7 and 0.3 and I add those two together, I get 1, right? So those are kind of compatible decimals in this sense. So one way I would rewrite this problem would be to try to add those two numbers together first. So I can do this in a couple of rudimentary steps. So I can just change the order of the addition. So this is by just commutativity. So I'm just doing this in baby steps here. So just changing the order of 4.3 and 3.2. And then by associativity, I can change where my parentheses are. So this is associativity. And now 1.7 and 4.3 we said are nice to add together because 0.7 and 0.3 make 1. So 4 plus 1 is 5, and then I'll add another one for that 0.7 and 0.3 to get 6. And I'm going to add 6 plus 3.2. That gives me 9.2. So this is kind of a written out way that we might do this mental math of looking at how I would add these three numbers more easily in my head. I might look at, kind of summarizing it quickly, just look at, 1.7 and 4.3, that adds to 6 because 1 and 4 adds to 5, and then I'll add one more for those decimals. And then I just have to add 3.2. So another nice technique that we didn't really have as far as the other mental math properties that we talked about with whole numbers, like compatible numbers, and properties like associativity and commutativity that we had before. Something we have now is being able to look at fractional equivalence. And so, for example, when I think of multiplying 68 by 0.5, it might help me to think of this as multiplying 68 times a half. And that's nice because I know that multiplying by a half is really the same thing as dividing by 2. So that's just 34. Similar type of thing, if I multiply 72 by 0.75, well, that's just multiplying 72 by 3/4. And that's kind of a weird fraction, but if I split it up as 3 times 1/4 times 72, kind of using associativity here. So I'm making 3 fourths 3 times 1/4 and using associativity. Then this makes this a little bit easier to compute. So I can take 72 and divide by 4 or multiply by a fourth, same thing, right? And that is just 18. And then multiplying that number by 3 gives me 54. So here we have this newer thing that we didn't have with whole numbers, where we can look at fractional equivalence of decimals, because sometimes it's easy to do things like divide by 2 or divide by 4, as opposed to thinking of multiplying by 0.5 or 0.75. Okay. Great. So last piece in this section of 7.1 that I wanted to chat about was this theorem that is very wordy and formal looking, but I'm sure you know and use very often, which is that when I multiply a number, so I'm thinking of any number n, so it could be any decimal. Let's see here. So I have any number n, and I multiply by 10 to the m. So this is some power of 10. I can do this by forming a new number, which is the number n, but moving that decimal point m places to the right. If I divide by 10 to the m, and this is assuming m is some positive number, I should say. If I divide by 10 to the m, I move the decimal 10 places, or m places to the left. So in other words, if I look at this example on the right here, 0.003 by 41,000, what I can do is imagine, I'll rewrite this out in kind of a few steps so it makes a little bit more sense. But how do I want to write this? Let's see, 3, this is really 3 times 0.001, and 41,000 is 41 times 1,000. So I'm just doing this to kind of illustrate what happens with the place values here. So this is all multiplication, so everything's commutative and associative, right? There's not any weird distributive property that I need to worry about, right? Because I have times, and times here, right? Okay, so this is the same thing as what I can end up doing, right? Is multiplying 3 times 41 by using my commutivity, and 0.001 times 1,000. And this 0.001 times 1,000 just tells me, when I multiply by 1,000 here, it's telling me to move this decimal place 1, 2, 3 to the right. Okay, and so in other words, this is what's telling me that this is just going to be a multiply by 3 by 41, which is 123, and multiplying by 1,000, multiplying 0.001 by 1,000 gives me that this piece on the right is just 1. Right, so this is 123. Okay, so obviously to do this problem, you don't need to write out this many steps to compute this, but this is kind of just illustrating what's happening with the decimal points. You can kind of see this theorem in action a little bit clearer if you maybe wrote out the fractional representation of these this 0.001. So that would be 1 over 1,000, which is just 1. Right, so maybe I'll write that. This is 1 over 1,000 times 1,000. That's why we're getting 1 there, right? Okay. So you've probably used this theorem often, but this is just kind of a formalized version of that theorem. In our next video, we're going to talk through section 7.2, so working through the operations of addition and subtraction and multiplication and division using on decimals. Okay.